Hello everybody, thank you very much for inviting me to give this presentation. It is really an honor and a pleasure to contribute to the SIMS program. Today I will talk about recent work on probabilistic analysis of neural networks, work that was done in the context of a larger project that addresses formal verification of neural networks. In this work, we analyze artificial neural networks, which, as you may know, are computing systems which are loosely inspired by the biological neural networks in animal brains. They consist of neurons, which are computational units organized in multiple layers. And neurons can be active or not. And for the neural networks that we analyze, which are typically classifiers, the last layers contain decisions. They perform feature extraction and input transformation. And as you may know, they learn, meaning progressively improve performance to do tasks by considering labeled examples. And the edges that you can see in the figure that connect the neurons have weights that are inferred based during this learning phase. And such networks can represent complex nonlinear relationships between inputs and outputs. But in our work, we analyze feed-forward neural networks that are piecewise linear. And in particular, we have looked at networks that use the ReLU activation function, which compares the value of neurons with a threshold, which is 0 in this case. And if the value is greater than 0, the output is set to that value, otherwise it's reset to 0. And also if the value is greater than 0, the neuron is said to be active, and otherwise it is said to be inactive. And as I said, our work also generalizes to any neural network with piecewise linear computation, including convolutional neural networks. And neural networks have found many applications. They can be used in pattern analysis, image classification, sentiment analysis, speech and audio recognition, medical diagnosis. And what is of interest for us at NASA in autonomy. For instance, neural networks have been used in perception modules for self-driving cars or in controllers for adaptive systems. But with this increased use of neural networks in different domains come also safety and security concerns. One such concern is lack of robustness. It is well known that small, imperceptible to the human eye changes to an input may lead to misclassifications in a neural network. And this can happen even for highly trained, highly accurate networks. For instance, if a street sign is modified by applying some stickers, its image may be mistaken by a neural network to be a birdhouse. Or as another example of this phenomenon, consider the image of a red traffic light, and by adding 11 white pixels, the resulting image can be mistaken by a neural network to be an oven. And you can imagine that such mistakes can have catastrophic consequences if such a neural network is used, for instance, in the perception of an autonomous car. Another problem that is also well known and well studied in the literature is the lack of explainability. Neural networks are essentially black boxes, and it is not well understood why a network gives a particular output. And this is a problem for certifying such systems, since it would be difficult, for instance, in the case of an accident, to place a blame on a decision from the neural networks. Another problem is scalability. Networks are very large, they are highly interconnected, often have huge input spaces. For instance, image recognition takes huge inputs as images, as matrices of pixels. And these characteristics prevent thorough verification or testing. And furthermore, many heuristics that were developed in the verification and testing community don't apply in the case of these highly interconnected structures. And finally, I list here another challenge, which is less studied in the literature, but we consider also very important, which is the lack of intent. So while typically safety critical systems are designed with clear formal requirements in mind, neural networks learn from examples, often without a high-level specification. And to address these concerns, we have started a project at NASA Ames called SafeDNN, which stands for Safety of Deep Neural Networks. And in this project, we explore techniques and tools to ensure that systems that use deep neural networks are safe, robust, and interpretable. And we have several research directions. So, for instance, with collaborators from UT Austin, the Safraz Khurshid's group, we developed symbolic execution techniques for the analysis of neural networks. Also, in another mini project that is part of this overall project, we are studying parallel and compositional approaches to improve formal constraint-based verification of neural networks. And in this mini project, we are collaborating with Stanford University, Clark Barrett's group. In another mini project, we have developed property inference techniques for neural networks, and I'll describe it in more detail a bit later in this talk. And currently, we are investigating automated program repair for neural networks. Furthermore, we are investigating probabilistic reasoning for neural networks, and again, I'll give more details later about it. And in some other recent work that was, in fact, presented last week at CVPR, which is a computer vision conference, we have investigated system-level explanations using the Cynic programming language developed at UC Berkeley. And the overall goals of our project are to provide strong guarantees with respect to safety and robustness for neural networks, with particular emphasis on use in autonomy, to obtain compact formal explanations of neural network behavior, and to improve testing, debugging, and maintenance of neural networks. I would like now to highlight some of the recent advances that we have done in our project. And all this work was done together with Divya Gopinath, who is also a colleague of mine at NASA Ames, and with various collaborators. So in the first item, I would describe property inference for deep neural networks that was presented at the ASC conference last year, and this was joint work with Hayes Converse, who was intern at NASA Ames last year, and also with Ankur Tali, who was at Google at the time of this work. And then I will describe a bit our work on developing a programmatic and semantic approach to explaining and debugging neural network-based object detectors. And this was done together with Edward Kim and his advisor Sanjit Seshia from UC Berkeley, while Edward was a NASA intern last summer. And then I'll give more details about our work on probabilistic analysis for neural networks. So for property inference for neural networks, the key idea is to infer likely properties which have the form of contracts, input-output contracts of a neural networks. And this is similar to DICON or other techniques developed in the software engineering community. And once we infer properties that are highly likely to be true, we then attempt to prove them using a decision procedure such as ReLUplex from Stanford. And in case this proof does not succeed, because, for instance, the network is too big or the input space is too large, we can still use the available training or test set to provide statistical guarantees about the inferred properties. And also, in case the properties are found not to hold, we can refine them automatically based on counterexamples provided by ReLuplex. So going back to a high-level description, so what is a property? A property is of the form sigma implies P, where sigma is a precondition and defines a safe region in which the network behaves safely or as expected, and P is a postcondition which specifies the desired output behavior. For instance, that the network has some desired prediction. And we developed two methods where we aim to compute input properties and layer properties. And the difference between them is that the input properties capture safe regions over the input space, while the layer properties characterize regions over the values of neurons at an intermediate layer. And the intuition is that neural networks work by extracting high-level features, which are captured the values of the neurons at intermediate layers. So we hope with these techniques we can infer properties over these high-level features. And we have developed two techniques. For to infer input properties, we use a form of symbolic or concolic execution, and then an iterative relaxation of path constraints. And we also use linear programming solving to compute under approximation boxes for these path constraints, which can then be easily visualized and interpreted. While at intermediate layers, we have a technique that uses decision tree learning over the on-off activation patterns recorded over using the training or the test data at given layers. And once we discover these patterns recorded with decision trees, as I said, we use ReLuplex to actually prove such properties. And on the right-hand side of the slide, I show a simple example. We have a network with two inputs, two outputs, and two intermediate layers. And I also show an input property, which is a convex region in the input space that leads to class 1, for instance. And it basically represents a conjunction of constraints over the input values. There are many applications for these properties that we infer automatically. So, of course, we can find adversarial examples because the counterexamples obtained with ReLuplex proofs represent inputs that are close to other inputs that are labeled differently. We can also generate explanations that have formal guarantees. So in essence, a precondition that was formally proved can show a mathematical relationship between the inputs and outputs. So effectively, it's an explanation of partial explanation of the network behavior. We have also used the infer property to build simpler models through a form of distillation. So here you can imagine that once you have these infer properties that are proven or hold with a high probability, you can use them instead of the forward pass of the neural network. And whenever an input comes and satisfies the inferred precondition, we can simply postulate the output without any other computation. And there are many other applications that I'm not listing here. So for instance, they can be used for runtime monitoring. So whenever an input comes and it fits into the inferred properties, we know that the neural network behaves as expected, but if an input comes and it is outside of the property, it can be rejected, or the application can go into fail-safe mode. And here I list some of the results we obtained for ACAS Xu, which is a controller for unmanned aerial vehicles, and I will give more details about this case ACAS Xu system later when I'll talk about other techniques. So I just wanted to highlight here quickly that we were able to discover novel properties for this system, which were validated by domain experts. We also used the layer patterns that we inferred with the decision tree learning to decompose hard proofs, which are of the form A implies B. So in fact, this ACAS Xu system does have some high-level properties that it is supposed to satisfy, but they are really difficult to prove. But with our layered patterns, sigma, we could decompose them into two checks, A implies sigma and sigma implies B, where sigma is a pattern at some intermediate layer, resulting in simpler, cheaper checks that were performed with reluplex. And all in all, this resulted in significant speed up obtained, and we were able to check properties that timed out with monolithic verification. And on the right hand side, I show some results for MNIST, which is a well-known data set that represents images of digits. And I can show here the under-approximating, a visualization of the under-approximating box for a property that we computed for output 2 for a network that was trained on MNIST. And also some an image of 1, which was misclassified as 2, and then again a visualization of the under-approximating box corresponding to it. And you can imagine that one can use these under-approximation boxes to draw more inputs that are similarly misclassified in order to understand the incorrect behavior of the network and also to retrain the network. And now I will go to the second highlight of the talk, which is the CVPR result. So in this work, we aim to extract semantic explanations of a detection module used in an autonomous car. So we analyze the neural network, which takes images of road conditions that have different cars, different obstacles, different light and weather conditions, and so on. And then the purpose of the network is to place bounding boxes around detected obstacles, and these boxes are then used by the controller of the autonomous car to try to avoid them. And the key idea in our work was to leverage these high-level semantic features, which are other cars, features that can be are present in a road scene, and they can be encoded at a high level in a scenic probabilistic program. And we use this approach to try to derive rules which are sufficient conditions that explain the module. So to explain the image, we start with the user scenario, which is a probabilistic program that specifies constraints and distributions over these high-level objects to be placed in the scene. And based on this user scenario, the scenic system generates feature vectors in terms of these high-level features, which are then input into a simulator whose renderer is used to generate realistic images that contain the features specified in the user scenario. And in our work, we try to refine this user scenario in an attempt to increase the misdetection rate, or on the contrary, the successful detection rate of the module under analysis, in order to understand why and in what circumstances it misbehaves, or on the contrary, which scenarios it can handle well. So the benefits of our approach are to better explain and debug the module. And we have developed different techniques, both black box and white box, that derive these rules that allow us to refine the cynic programs to obtain explanations of good and bad behavior of complex neural networks. And I should say that in this paper we went beyond piecewise linear neural networks, but we didn't prove the rules that we derived, but we used statistical analysis to get confidence into the analysis. And here are some of the results that we obtained. So on the left-hand side, I showed some rules for correct detection, and on the right-hand side, some rules for incorrect detection. And you can see that, for instance, we started with a scenario that has had 65.3% success rate, and by refining it, by adding the rule that specifies more constraints on some of the important features in the program, for instance, x coordinate is greater or equal than a certain value, we were able to increase the correct detection rate to 89.4%. And furthermore, for incorrect detection, we started with scenario 1, which had 34.7% incorrect detection rate, and we were able to pinpoint the cases when the network misbehaves. So we increased the misdetection rate to 87.2% by adding rules about the coordinate, the distance, and the particular car model of the obstacle that is placed in the image. And this information can be used by a developer to understand in what situation the neural network detection fails. And one can then try to improve it by retraining, or perhaps fall back on a different detection module that would work better in these particular conditions. So now I would like to give more details about the main topic of this presentation, which is about probabilistic analysis of neural networks. And I'm also showing here the pictures of myself and also my collaborators, who are again Divya Gopinath from NASA Ames, Hayes Converse from University of Texas at Austin, who was a NASA intern for the past 2 years with us, and also Antonio Filieri, who is a professor at Imperial College London, and he was also visiting us last year. And we were hoping to see them again, but because of the virus situation, everything now is virtual. So the motivation for this probabilistic work is as follows. So in the past, both ourselves and other researchers have performed extensive research on trying to prove properties of neural networks. And in our work, we try to use Reluplex and its successor, which is called Marabou from Stanford University. And we have an ongoing collaboration with them. But we found that in practice, properties often do not hold. So, or if they hold, they only hold in tiny regions around inputs. And usually, actually, the majority of formal verification for neural networks is done for proving pointwise robustness of neural networks, which basically check around an input point that the network gives the same decision. But such formal verification tools can output only binary answers and lack detail, which may be unsatisfactory. And furthermore, verification tools in general do not scale for large networks. There is a lot of promising work in that area, but they still cannot handle most realistic networks. On the other hand, we think probabilistic properties are more natural. For instance, accuracy, which measures how well a network generalizes to unseen examples, is of course a probabilistic property. And in general, neural networks are approximate techniques that people use them expecting to perform well most of the time, while perhaps certain small errors are tolerable. So such properties can be checked with statistical methods which scale but provide few guarantees. And also they tend to ignore rare events, which may be important for safety critical systems. So in our work, we propose to amplify a statistical analysis through a more rigorous probabilistic analysis. And the goal is to increase the impact of the samples used in the statistical analysis, and also to provide a precise measure of confidence in the results. And in our proposed method, amplification is achieved through symbolic execution and also volume computations performed over the mathematical constraints collected with symbolic execution. And amplification is achieved in two ways. So we collect neuron activation patterns along each sample. And thus, a sample is amplified to represent all the samples that follow the same pattern. And furthermore, the activation pattern obtained for each sample is appended with all the possible decision conditions one by one. And thus, one activation pattern is amplified to multiple constraints, one for each decision condition. Thus, if we have an input or a sample that leads to one output in the neural network, it is possible that another input that follows the same activation pattern can lead to a different decision condition. And we can catch it by appending it to these decision conditions. So in some sense, we amplify the effect of local robustness checks using these symbolic constraints. And furthermore, we maintain an efficient data structure that records all the samples that have been performed so far to enable rejection sampling for increased scalability. And to give a bit of background on the approach, as I said, we use a form of symbolic or rather concolic execution, which is a well-known program analysis technique, which has been used extensively in the software engineering and the programming languages communities. And this technique assigns symbolic values to inputs, and at each branch it updates path conditions that maintain constraints on the inputs, and the solutions to path conditions form test inputs for the paths. And here is an example of how symbolic execution could be applied to neural networks. So on the left-hand side, on the top, I have a small neural network with two inputs, two intermediate layers, and two outputs. And this example is actually taken from a study on fairness analysis for decision programs. And you can view such a network as a program or as a traditional imperative program where each activation can be seen as an if-then-else condition, which compares the values of incoming values at each neuron with 0 and forward that value or reset it to 0 depending on whether the value is greater or not than 0. And on the right hand side on the top I show the symbolic execution tree, which is built naively by essentially recording all the possible on-off combination of neurons in the small neural network. As you can imagine, this would be very inefficient for large networks, so we actually devised a more efficient data structure where for each layer of the network we define its activation pattern as a bit vector whose nth bit represents the activation state of the nth node in the layer. And here the nodes in blue have been represent nodes that have been activated by at least one sample input, while nodes in red have not been activated by any sample. So I show them here just to illustrate that the tree is pretty sparse. And our data structure takes advantage of the fact that all neurons at the same layer of the neural network are independent of each other. So the activation patterns at a layer do not have an ordering. They can be considered in any order. And also, I want you to know that the tree is prone to obtain a compact representation and enable early rejection of the inputs. So for instance, the two leftmost blue nodes in the tree corresponding to layer 2 are replaced with -0, indicating that both the on and off activations have been explored for the first neuron in layer 2. So for instance, when we generate a new sample and it has it doesn't matter what activation it follows for the first neuron, but it has 0 for the second neuron, then we can safely reject it because that was already seen before. So to summarize our technique, we collect activation patterns, which are neuron on-off patterns, and they form a partition of the input. We symbolically or rather concolically execute concrete inputs. We reject inputs that add no new information, meaning we reject the inputs with previously seen activation patterns. We add decision conditions to constraints based on network output, meaning the logis layer, and this allows us to amplify further the effect of the analysis for each sample. And then we compute the volume of the collected constraints, where the constraints correspond to the mathematical conditions imposed by the activation pattern, which compare the symbolic expressions that flow into a neuron with 0. And then the analysis is anytime it improves precision with more samples, and it stops at a user-defined criterion, for example, coverage achieved or number of paths, symbolic paths explored, or a rejection percentage, and so on. And this is similar to previous work on probabilistic symbolic execution, but it has been adapted to the particular characteristics of neural networks. And for volume computation, we use off-the-shelf solutions available. So I should say that while previous work on probabilistic symbolic execution mainly handled integer constraints and used Barvino correlate as decision procedures, for neural networks we had to look for volume computations over floating point numbers. So we found a tool called Vinci, But it is expensive in practice, so we have developed some optimizations. So for instance, we can sort activation patterns by hits versus a new set of inputs to cover more space quickly. And we also have a novel use of an interval solver, namely RealPaver, to compute sound intervals, which are under and over approximating solution boxes over the collected constraints. And once we have these boxes, we can easily estimate their volume. And then we use that in our analysis. And I should say that RealPaver can also handle nonlinear constraints. So in principle, this work would go beyond the piecewise linear neural networks and could handle arbitrary networks. And here I give some information about the input distributions and the computation of probabilities. So first, notice that if we assume that all the inputs are uniformly distributed, meaning they are equally likely, then we can compute the probability of the network to give a certain decision D by simply computing the volume of the constraints for the paths that lead to D over the volume of the full domain. But we can also handle arbitrary non-uniform distributions by partitioning the input domain and creating a histogram distribution of the form SI-PI, where SI is a subset of the input domain and PI is the respective probability. And then I show here the formula for computing the probability of event D using these histograms. And here AC are the activation conditions, which are appended with the decision conditions leading to the event D. And finally, a note about the confidence values. So confidence here is simply the percentage of the input domain covered by the analysis. So this would give us precisely how much of the input domain we were able to cover. And if the confidence is 1, it means we were able to cover the full domain of the problem, assuming, as I forgot to say, that the domain is can be very large but finite. And we have implemented the techniques in Space Scanner, and we have applied them for the robustness or sensitivity analysis for ACAS Xu, which is a family of neural network controllers developed for the next generation airborne collision avoidance systems for unmanned aircraft. And we analyzed one network from this family. And here robustness or sensitivity means that we want to analyze how well the controller performs if there are small perturbations coming to certain inputs. And the analysis can also be applied for fairness, analysis of decision-making networks, but I will not cover that here. So a bit of background on ACAS Xu. This is a safety-critical collision avoidance system for unmanned aircraft control. It has 5 inputs that come from sensor data about the ownership. And they are the range, angle of intruder relative to ownership, heading angle of intruder with respect to ownership, speed of ownership, and speed of intruder. And we analyzed the network with 6 hidden layers, 50 ReLU nodes per layer, and 5 outputs or labels, which are the advisory for the ownership, and they that can be used to avoid collision with the intruder. And these outputs are clear of conflict, weak left, weak right, strong left, and strong right. So we evaluated local robustness for ACAS Xu which basically checks for a given input x that for all other inputs denoted with x prime, where the distance between x and x prime measured in some with some norm, for example in the Euclidean space, if this distance is less than an epsilon, then we expect the decision of the network to stay the same for both x and x prime. And while one can encode such formal proofs with a formal verification tool, the result can only indicate that an adversary is present or not. But in our work, as I already mentioned, we aim to quantify how robust or how sensitive is a network to perturbations. And in our work, we used some domain-specific knowledge that the experts told us that we only need to vary the first two parameters, while the last three parameters of the network had to be fixed in order for the examples to make sense. So this allowed us to simplify a bit the problem, which was still very difficult. And here are some of the results of our analysis. So we used 5 inputs per label, and we relaxed for 2 dimensions by 5%. And then we generated 10,000 inputs from within this relaxation by 5%. And then we computed several statistics. So for instance, the average rejection rate is about 91%, indicating that our tree data structure is pretty good at rejecting samples that essentially don't bring any new information. The confidence in the results is also pretty high, greater than 90%. The average volume computation is within minutes. And at a high level, we identified areas in the input where the network lacks robustness. But perhaps the most interesting result is that although statistical analysis produces comparable results, and also it's actually much more scalable, it does miss some cases when the probability of misclassification is non-zero. So for instance, for an input that was supposed to have label 4, the computed probability for hitting label 0 was greater than zero, non-zero, while the statistical approach gave a 0 probability. And similarly, for another input that was supposed to be labeled 1, the computed probability for label 4 was non-zero, while again statistical analysis gave 0. So although these probabilities are very small, they may be important for safety critical systems if in certain situations such a probability is bad, especially for, so 0 and 4 represent yes. So more results, we found that the network is highly robust in assigning clear of conflict decisions, and the probability of obtaining clear of conflict around most inputs was 100%. We also identified some spots with 20% chance of misclassification to weak right or weak strong, strong left. We found the network to be more vulnerable to adversarial perturbations for the advisories weak left, and strong right. And we also performed the targeted robustness against misclassification to certain advisories. And we found that when the desired advisory is weak right, and an adversarial advisory will only be strong right or clear of conflict, but not the advisory to turn in the opposite direction. So this again suggests that the network that we analyze is pretty robust and perhaps ready for use in a safety critical domain. To summarize, these latest results, we believe that probability properties are natural for neural networks, which are approximate in nature. Statistical techniques are scalable, but they do not provide strong guarantees and may miss low probability events. Also, amplifying inputs through symbolic constraints enables more accurate probability estimations and quantified confidences. And the analysis that I presented is useful for both robustness and fairness analysis. And some of the directions that we are currently pursuing include the use of model counting to quantify likelihood of rare events in neural networks. We are also investigating the use of model counting and volume computations to try to quantify the learnability of a model. We are also investigating automated debugging and patching for neural networks, and we aim ultimately to relate the properties of neural networks to the system level properties of an autonomous system using perhaps compositional techniques and assumed guarantee reasoning. And with this, I would like to thank you very much for your attention, and you can find more information about our project at the following website. And now I would like to listen to your questions. Thank you very much.